run. So welcome to another edition of the Hottest. And today we have a great pleasure of having Floris van Doorn, who will speak about formalizing a proof of Carleson's theorem.
Thank you, Chris. Yeah, so thank you very much for the invitation to speak here. It feels a little bit weird to speak about this topic in the homotopy type theory seminar because I will be talking only very little about homotopy type theory, but I think because this is like we're doing formalization and like there's very strong connections between like formalization and homotopy type theory. So I hope this result and this project is still interesting to all of you. Yeah, so this is a large project with a lot of collaborators. Some of them I've listed here. So it's joint work with Lars Becker, Leo Dietering, Asghar Janasham, Rajula Shrivastava, Jeremy Tan, and Christoph Thiel, and many others. So many of them are part of the Bonn harmonic analysis group. But then for the formalization, there's actually many other people that joined, which I will describe. So in my talk, because I don't only want to talk about Carleson's theorem, I also want to start with some highlights and latest results about Lean. I think all of you have like heard of Lean before, especially in the Lean 2 days when there was a dedicated homotopy type theory mode. And even though there's not like privileged homotopy type theory mode, I think there's a lot of like exciting developments in Lean. So I'll start with that. Then I'll discuss the mathematics of Carleson's theorem and Fourier analysis. And then I'll discuss the formalization and some practical issues that arose during the formalization. So Lean itself started development in 2013, but like all the hype is now in the latest version of Lean, which is Lean 4. So like the Lean community was still like happily working with Lean 3 and doing mathematics in Lean 3 for many years since 2017. But the development team already like transitioned into like developing Lean 4 since 2018. Even though that was when like the mathematical library of Lean like barely got started, that was in 2017. And so while that mathematics was developed, like Lean 4 was being developed. And so that took like 3 years before the first official release, which was in 2021. But then it still took quite a while, like more than a year before like it was really ready for MathLib. And so in like the end of 2022, we started like porting this MathLib from Lean 3 to Lean 4, which was like a very big project. It took about 8 months to do that port because MathLib had grown in those 5 years, like from almost nothing to like more than a million lines of code, doing mathematics, like with mathematics in like all kinds of areas. And so it took 8 months to do all the port from Lean 3 to Lean 4 because the syntax is quite different. Like there's a lot of internal changes. And so this was a huge effort. So Mario Carneiro had written a tool to do some automated porting from Lean 3 to Lean 4, but that was only an approximation. And so there was still like quite a lot of manual fixes that were needed. But we really wanted with the community to avoid like a split of some people still using Lean 3 and some people like moving to Lean 4. So we really put our effort into like doing this port and making sure everything got ported. And that indeed succeeded. Like after, like in the middle of 2023, we finished the port. We officially made like the lean free version of Mavlib deprecated and froze it. No new contributions are accepted there. And now we're in a very happy state where like there's every month a new version of new release of Lean, which with like exciting new features. And yeah, almost nobody's using Lean free anymore. And there's still a lot of activity in Mavlib. So Mavlib continues to grow. It's now more than 1.5 million lines of code. And there's still like a lot of activity every day. So here are some of the features that are like new in Lean 4. So Lean 4, besides a proof assistant, is also like a functional programming language. So you can also just use it as any other programming language. Like it's performant, it works very well, and has some like interesting like programming like perspectives from a programming language as well. One thing that is nice is that basically all the components of Lean are implemented in Lean itself. So things like elaboration, like figuring out all the implicit information you don't give the proof assistant that the proof assistant has to figure out, things like implicit arguments and type classes, and but also executing tactics like the pretty printer. All these things are implemented in Lean itself. Mavlib also uses quite a lot of these features, like it defines its own custom tactics for like domain-specific reasoning or like useful reasoning steps. It defines a lot of notation and pretty printers. And it has also like quite a lot of like linters. So for example, this can just be like syntactic linters. For example, if you have a long line or something, but also like semantic linters, things that sort of ensure that like Mavlib as a whole coheres. So for example, there's a simplifier in Lean that where you write like simp, and that will simplify like expressions to like some kind of normal form. And then we have a tactic that ensures that, for example, all these simp lemmas can actually fire, that they are not obsolete by other simp lemmas, and that they don't like result in some kind of infinite loops, things like that. There's also
Sorry, quick
a lot of
question.
work.
Yes.
Yes.
I think I have a sense of what the linter is. So for instance, I believe there's one that checks to see if all the arguments are actually used in your
Yes.
theorem, but I don't have any idea what a pretty printer is.
I mean, it's just like the thing you would see in the goal view. Like so if you write in Lean, you write some like tactics, for example, and then you see the proof state in the middle. So some of that is just like just notation, but you can also have like macros. So for example, if you want to print like existential quantifiers, if you want to like, you can, for example, tell Lean, oh, if you have a term of the form, like there exists a natural number n such that n is smaller than 5 and something else holds, then if you want, that can be printed like there exists an n less than 5 such that something holds. There's also like there's a lot of flexibility. Like there's also people that have used like some similar things where you can like write like you can implement like a Rubik's cube, and then it will like print like a Rubik's cube in like HTML, and you can like solve it with tactics in Lean. I mean, that's slightly different than the pretty printer. Yeah, so another thing that Lean really focused on was performance. So in the Lean 3 days, like at the end of Lean 3, we were really pushing like our library size sort of caused like quite slow compilation if you wanted to compile the whole library. And we really noticed that, for example, also when like merging commits and things like that, we had to like it took like like machines about like an hour to compile all of mavlib, and so we want to make sure that like the latest version of mavlib always compiles. So you need an hour for every commit, and that takes that is quite hard to work with. So we used software to like bundle commits together and then run like make sure that it compiles, but we still like stretch the limits. And now in Lean 4, like on a powerful laptop, you can compile all of mavlib like in 20 minutes. So it's still I mean, so very fast is of course relative. It's very fast compared to Lean 3 if you compared to simpler proof systems like Holite or MetaMath. I think they are a lot faster. Yeah, then I listed a bunch of like other features that I won't go in detail for all of them, but like there's like very nice integration in especially VS Code, but also some other editors where like there's, for example, code actions where you can tell Lean, oh, in this particular case, like you can give the user the option just by mouse button to like insert particular code in the text editor. So for example, there's an induction code action where you write like induction on n, and then it will like automatically generate the cases. So like this is very similar to, I think there's keyboard shortcuts in Agda where you can just do a case keyboard shortcut, and then you get like the pattern matching cases for that variable. Yeah, and another feature that was relatively recently added is incremental compilation. So if you in Lean 3, if you were editing a proof, then whenever you made a change in the proof, like it would start compiling the proof from the start. And because Lean was quick, that was often fine. But for long proofs, this definitely got annoying. And now there's in Lean 4 there's incremental compilation. So it will just, if you edit like a proof, like it will just start compiling from that point in the tactic proof. There's also an efficient code generator. So you can, if you write your tactic, you can compile it down to like C code, and that will like efficiently run your tactic, which is nice and used for like all of the built-in tactics in Lean. So now I want to move on to some of the exciting projects that are happening in Lean. So the first two I especially want to include because they are closest to the Homotopy type theory crowd. So Emily Reel is leading the Infinity Cosmos projects, formalizing like infinity category theory and infinity cosmoi, which sounds very exciting. Then Sina and Steve Audi and Mario Carnero and others are doing a formalization of the group model in HOT. And so their vision is to then have some kind of front end so that you can use like Lean as still some kind of proof assistant that you can compile and where if you then write a term in Homotopy type theory that will sort of be compiled to like its interpretation in the group-wide model, and then like it will actually become like something that the Lean's mathematical library can then work with, and so you can then reason sort of within mathlib with HOT, which looks very exciting. Then there were some recent formalization projects. So Terry Tao started formalization of some result in additive combinatorics. This is called the polynomial Feynman-Richa conjecture. And so the statement is about like if you have like some subset of an of a group which then you can sort of bound you can sort of look at how Okay, maybe let me skip the precise statement. If you want to know the precise statement, just Google it and you can find their paper. But it's a result in additive combinatorics. And what's interesting, this was proven like last year by Terry Tao and Tim Gowers and two other people, and was put on the archive. And then before it was like submitted for publication, Terry Tao said like wanted to formalize this in Lean. So he led like a project to do this formalization, and quite a few people joined, and like it was formalized within 3 weeks. So that was really nice that we could formalize like a modern research result in 3 weeks. It was of course like quite cherry picked because I mean it didn't use like deep techniques and was like it fit well on top of Mavlib. Like most of the preliminaries were already in Mavlib. Then there was another project led by Alex Kontorovic and Terry Tao, the prime number theorem plus project, which wants which has already formalized the prime number theorem in Lean and wants to prove some strengthenings of the prime number theorem. So this is talking about the distribution of prime numbers, like what fractions of the first n numbers are prime. Then a completely different result that I find very exciting is that is out of Google DeepMind. They used like a neural net work to try to solve problems at the International Mathematics Olympiad. And they had like two systems, one for geometry problems and another one for like generic problems. And they used then like a neural network together with Lean as a backend to like try to find formalizations of like these IMO problems. And they managed to, with like reinforcement learning and generating like synthetic problems, solve two IMO problems using Lean, and then they solved 4 problems, 3 in Lean and 1 geometry problem with another tool. So they did really well at IMO level problems, which I thought was not going to happen anytime soon. So that is really exciting. Then there are some ongoing projects. So Kevin Buzzard is starting already for a while, but this month it really started a project to formalize Fermat's last theorem, which is like a proof that is like thousands and thousands of pages separated over hundreds and hundreds of papers. So that is a gigantic project that will take many years. Then another project that was started by Terry Tao only 2 weeks ago is a project called Equational Theories, where he where basically the goal of this was, can we enable like large scale collaborations using Lean? So the question that is being asked is like, suppose you have magma. So this is just a set with a binary operation where you don't assume anything, not even associativity. Now you can add like like laws like associativity or commutativity or like any expression that you can write down using this binary operation. And you can ask like which of these laws implies which other laws. And the goal of the project is like, suppose you have all the laws that take at most 4 or 5, I don't remember right now, I think 5 occurrences of the operation, then you have like 5,000 different laws you can write down. And what is the complete implication graph between those 5,000 laws? And in the last 2 weeks, like there's been a lot of activity by a lot of people that joined, and I think they're now like out of like all the possible like 5,000 squared implications. They've done now 99.999 something percent. And I think there's now still like about 500 equations that are open, which are of course like the hard equations because there's many trivial ones. But I think that is also really nice to show how Lean sort of can help do large scale projects. And then in the rest of the talk, I'll talk about a project that I started, which is the Carlesons project, doing some interesting harmonic analysis, which is also like a big project because the Carlesons, so the project is, the goal is to formalize Carlesons theorem, which is like a famously difficult theorem in harmonic analysis. And so, for example, there's, as far as I know, there's no textbook that like has the proof. You have to go to like research papers, even though it was a result from the 60s. So, so the Carlesons theorem is actually quite simple to state, but before I state it, I'll take a step back and like refresh your memory on some Fourier analysis. It has probably been a while since of you worked with it. Let's start with if we have a periodic function. So we have a function, well, I can say it's either a periodic function on all of the real numbers, or I can just say it's a function that is just on like a finite domain, and then you can sort of extend it periodically. So I have a function, say from 0 to 2 pi, or the circle to the complex numbers, and I'm only assuming it's integrable, not necessarily continuous for now. Then I can define its Fourier coefficients, and then so this, you do this by multiplying the function by like some complex exponent with like n times x in the exponent, and you integrate that over where f is defined, and then there's some normalization, and that gives you the Fourier coefficient, and that gives you sort of like, oh, how strong is the frequency in that how strong is that frequency in the function. And then from these Fourier coefficients, you can try to build up the original function. So you can, by taking the sum of the Fourier coefficients and multiplying that by these complex exponents. And of course, this complex exponent, like it's built up from like cosine in the real part and an I times sine in the complex part. So that's where the frequencies come in. And so for nice enough functions, like these Fourier series converge to the original function. For example, if your function is continuously differentiable. So this is like a very explicit formulation, but doesn't really tell you why the Fourier transform is so important. So let me take a step back and more abstractly tell you what this Fourier series is. So Fourier series, you should really think of as like decomposing a function into like basic functions. Like in the same way here on the right, if you have a vector, like here you have a two-dimensional vector, but if you have a vector in Rn, you can build like you can decompose it into like multiples of like basis vectors. So you have few basis vectors like E1 and E2 of the plane, and you can decompose like your V as a vector in the direction of E1 and a vector of the direction of E2, and then it's the sum. And with the Fourier series, it's the same, except you have an infinite dimensional space, like, or a Hilbert space. So to make that precise, we work in like the L2 space. So these are the functions who are square integrable. So if you take the function, if you square it, then it must be, the integral must exist when you take the integral from 0 to 2 pi. And then we take as a basis for this L2 space, and I should be, maybe if I want to be very precise, this is the L2 space is only is quotiented. So two functions are equal if they are almost everywhere equal. So the measure of points where the functions is not equal is null, has measure 0. And so the basis factors here are these functions that send x to e to the I and x for integers n. And these form an orthonormal basis. You can check that quite easily. That if you take an inner product between the two, so maybe I should mention, can I draw? Let's see. Can I draw on the screen? I don't see it easily. Okay, that's fine. But so this L2 space is an Hilbert space, so it has an inner product, and the inner product is just, if you have two functions, then you multiply the functions and you integrate that. That gives an inner product, and under that inner product, this is an orthonormal basis. So if you take they all have norm 1, and if you take two different ones, then their inner product is 0, so they're orthogonal. And moreover, these functions have a very nice property because they are the eigenfunctions of the differential operator. So if you apply the differential operator to these functions, you get just a multiple of your original function back. And this means in particular that if you take the Fourier coefficient of the derivative of a function for like a nicely differentiable function, then it's just a multiple of the Fourier coefficient of the original function. So you have this very nice relation, and this sort of hints at why the Fourier series is so convenient, because it allows you to turn basically differential equations into polynomial equations. If you have a differential equation, that's really hard because you have all these derivatives. But if you would take the Fourier transform, then it just becomes a polynomial equation, which is quite a bit easier. So that is sort of the idea why Fourier series are so important. But actually, in practice, you often don't just want Fourier series because Fourier series are for periodic functions. We assume that the function was periodic or only at finite domain. But we want to also deal with functions on all of the real numbers that are not periodic. And then you have, the situation is a bit more difficult. But you can still take then the analog, which is the Fourier transform. And one reason why this situation is a bit more subtle is that now if these basis elements that map x to e to the I and x, they are not square integrable on R anymore. Like if you take they have norm 1, and the constant function 1 on all the real numbers has of course an infinite integral. So these functions do not live in the L2 space on all of the real numbers anymore. So that's why it's a bit more subtle, and that's why now with the Fourier transform you have to take an integral to build back the original function. So here's the definition of the Fourier transform, and I highlighted everything that is different with respect to the Fourier series. So the definition is actually quite similar, but there's a couple of key differences. So now the function is on all of R, not just periodic or on a finite domain. And now the Fourier transform is again a function, a complex valued function on, say, the real numbers. And now on a value xi, it has like this exponent I times xi times x. And I'm adding a 2 pi just for convenience. And now we're integrating over all of R. But so the formula is essentially the same, except that in the exponent, before we only had integers, now we have an arbitrary real number. And in the inverse Fourier transform is also pretty similar to the Fourier series, except instead of the sum, we now have an integral. And what's actually nice is that there's now kind of a symmetry between the Fourier transform and the inverse Fourier transform. They're actually basically the same, except that there's a minus sign in the Fourier transform that you don't have in the inverse Fourier transform. Yeah, and so the Fourier transform still has some quite nice properties. So at least if your function is nice. So if your function is like continuously differentiable, then the Fourier transform behaves very well. So for example, if you take the Fourier transform of the derivative of your function, then that is just take the Fourier transform of the original function and multiply it by psi and some constants, some complex imaginary constant. And we also have this, which is the Frea inversion formula, which actually says that, well, the inverse Fourier transform is actually an inverse of the Fourier transform, at least on continuously differentiable integrable functions. So this says if you take the Fourier transform of f and then take the inverse Fourier transform, then like at every point, this is the same as your original function. But we often deal with, we often want to apply the Fourier transform to functions that do not satisfy these properties. So for example, if you just start with a box function, so f is just a box that is just 1 on the interval from -1, -1/2 to 1/2, and 0 everywhere else, then its Fourier transform, so this is definitely not a continuous function, and its Fourier transform is this function, basically sinus xi over xi, up to some constant. And the Fourier transform is not integrable. And that is a small problem, because if I go back to this definition of the inverse Fourier transform, like I was taking an integral of this function, so I cannot even apply this definition of the inverse Fourier transform to the function. Yeah, so it's not absolutely integral, to be more precise. But so on finite intervals, it is still integrable. And so we have to change the definition a bit to be a bit more precise, namely by taking the integral on like finite intervals and then letting those intervals go to infinity. So so that's what so we have to deal with improper integrals. So we can define for any like locally integrable function, in particular all continuous functions, we can define the Fourier transform and the inverse Fourier transform by just taking the integral over like a finite interval and letting that interval go to infinity. And there's an important thing you have to realize here when taking this limit, and that is that you can choose different topologies with which you can take this limit. So you can take this limit pointwise. So for each psi, you can compute this integral and then like let r go to infinity. Or you can just think of whatever is inside this limit as a function of psi. And then you can use some topology on function spaces to look at what is the limit. So in particular, there's a notion of LP convergence. So the LP convergence is take the function, takes its absolute value to the power p, and then integrate that. And then, so that is the LP norm of the function to the power p. So then you have to take it to the power 1 over p to get the actual LP norm. And so what you can also do is look at these integrals and see if they converge with respect to like any of these LP norms. And whether it converges or not depends very heavily on whether you use like the L2 norm or like the pointwise norm, as I will show in the next slides. So if you use the L2 norm, then everything is actually very nice. So then basically this idea that L2 is also L2 is still a Hilbert space. You still have the issue that like you're now splitting it up into these exponentials that do not themselves live in L2, but yeah, because it's a Hilbert space, you can actually still use like all these techniques. And so whenever you start with a function in L2, then you can take its Fourier transform using these improper integrals. And then that is again an L2 function. And then the inverse Fourier transform applied to that is equal to your original function with respect to the L2 norm. So this limit I showed on the previous slide should then be taken with respect to the L2 norm. But for if you want pointwise convergence, things get quite a bit harder, and that is what Carleson's theorem is saying. So, so I already mentioned earlier, if your function is like nice and smooth, like so continuously differentiable, then the Fourier transform, the inverse Fourier transform is actually an inverse of the Fourier transform also with the pointwise topology. But if your function is less smooth, like if it's just continuous or if it's just like L2, then you don't get that for every point, but the Carleson theorem says you still get it for almost every point. So on a set of measure 0, it might still diverge, it might do crazy things, like the limit might not converge, or it might converge to a different value. But for almost every point, the inverse Fourier transform pointwise converges to the applied to the so the inverse Fourier transform applied to the Fourier transform converges pointwise to your original function. And you can slightly generalize that this was so yeah, Carleson's theorem was proven in 1966, and then it was generalized a bit by Richard Hunt in 1968. That says if you don't start with an L2 function, but with an LP function for P strictly greater than 1 and at most 2, then you have the same results. And so, yeah, so these LP functions for P less than 1, so LP functions sort of specify two properties of a function. So a function fails to be LP if either it has like very large peaks, and then like in that interval where that peak is, like the function is not integrable. And for peak, it holds that the higher the p is, the harder it is to be LP. Because if you take a large number and take it to a large power, it will get even larger. And the other thing that what might fail function to be, what might cause a function to fail to live in LP if it has like a long tail. So if it doesn't tend to 0 quickly enough, if its input tends to infinity. And in that case, the lower the p is, the harder it is to be an LP, because if you have a number that is like between 0 and 1, like for a very large p, then if you take it to the power p, you will get a number that is much closer to 0. But if you take it to a very small power, then it's like your tail must decay even more rapidly before the function, for a function to live in LP. And so, so this is a stronger result because for LP for P between 1 and 2, this means that this holds also for functions with like higher peaks compared to L2 functions. Yeah, and so I already mentioned these theorems like are notoriously hard. So I can give you some indication why these problems are hard. So in particular, so for one, we cannot remove the almost everywhere from the statement. So even if we start with a continuous function, then like the limit might still diverge in some set of measure zero. So even for continuous functions like this like the inverse Fourier transform might not the Fourier transform and then the inverse Fourier transform might not give you the same function back everywhere, just almost everywhere. And the other thing is, like in this second result, I said that P must be strictly greater than 1. And that is really necessary because for L1 functions, then it's possible to have a function where just the integral that, the limit defining this expression just diverges everywhere. So then you don't get like anything that is resembling your original function. And so for exponents like close to 1, like the like this expression can still be like quite radically behaved or converge slowly to your original point. Yeah, so what I mentioned here is the Carleson theorem for the Fourier transform, and there's also like a precisely analogous formulation for the for periodic functions and taking the Fourier series. And even for the Fourier series, like if you just have an L1 periodic function, then that could also fail. And another indication why this might be hard is that I've done everything so far for real valued functions. And like Fourier transforms, you can define in the same way for functions in multiple variables. But actually that makes Carleson's theorem also very subtle, because then you have to like also choose an integration domain. For example, in R2, you have to choose some domain in the plane and then like blow up that domain to become larger and larger. And actually, whether Carleson theorem holds depends on the shape you choose. So if you choose rectangles, or boxes in higher dimensions, then Carleson theorem still holds and generalizes. But for example, if your shape is spherical or hyperspherical in more dimensions, then it's still an open problem, whether like this result holds or not. So like it's a very subtle problem. So to give you a sketch of the proof, so the idea behind the proof is that you have you define like a Carlson operator. So that is a sublinear operator given by this this expression. So this expression is similar to the integral for the Fourier coefficients of a function, except that you multiply it by 1 over x minus y. And this is called the Hilbert kernel. So this is, you multiply it by like some function that like decays if x and y are very far apart. And the other thing is you don't take this integral just once, but you take the absolute value and then you take the supremum over all like all Fourier coefficients, basically all integers n. And so this is not a linear operator in F, but because of the absolute value and the supremum, it's only sublinear. So this operator applied to sum of two functions, it's less than or equal to the sum of the operators applied to the individual functions, but it might not be equality. And I'm lying a little bit in this equation, which I'll come back to in the next slide. So that's why this is only roughly equal. But the idea is that this operator is a bounded function from L2 to itself. So what that means is that the L2 norm of like the operator applied to F is at most some constant times the L2 norm of F, and this constant of course doesn't depend on F. And then from this you can show that Carleson theorem follows from this the boundedness of this operator. That is not trivial, so I won't describe it here, but that is what the original proof does, and every proof since has also done. So you want to prove that this operator is bounded, So one thing I didn't mention yet, we are not just formalizing Carleson's theorem as Carleson formulated it in the 60s, but we actually formalize much more general results that was found by the harmonic analysis group here in Bonn. And so that was the reason sort of why we started the discussion of this formalization. So the pitch is we're formalizing Carleson's theorem, but we're actually formalizing like a result from last year that has not yet been published, but was found last year. And so let me describe some ways in which we generalize it. So this is this Carleson's operator, and I'm lying here because in this integral, we're integrating over y, but actually for y equals 0, there's a problem because you're dividing here by 0, and this integral actually doesn't exist. So you sort of have to cut away 0, and similarly for infinity, this might also not exist for all functions. So we also cut away at infinity. So what we're actually doing is we're just looking at all the values where x and y are within a range between R1 and R2, and then we just take the supremum over all possible R1 and R2, which are real numbers, positive real numbers. So that is what my lie was about. So we have to be careful with like our domain being containing x, where this function has a pole, and when y goes to infinity. And so we're doing it this way. And now in the generalization, we can generalize quite a few things. So I mentioned that this Hilbert kernel, this 1 over x minus y, and actually there is in harmonic analysis something called a Calderon segment kernel, which is like a characterization of like these binary functions with some properties, and you can actually do this for any of these kernels. And so a Calderon segment function is like a measurable function that takes two arguments that satisfies like some binary conditions. So like it must decay like somewhat rapidly if x and y are far apart from each other, and it must also not oscillate too quickly. So we can change this factor into a kernel. Then also in this exponent, we're now taking like linear functions in terms of y here in this exponent. But there's also something called the polynomial Carlesons operator, where instead of a linear function in y, you take a polynomial. And in fact, the generalization is that we actually allow a wide class of functions where so-called compatible functions, which roughly say, oh, these functions behave a bit like polynomials. And then we modify this exponent. And the last thing is we don't want to just do this for the real numbers, but we actually work on a much more general space, a so-called doubling metric measure space. So this is a metric space with a Borel measure, which satisfies a doubling condition. So that means the measure of a ball with radius 2r can be bigger than the measure of a ball of radius r, but not too much. And, like a ball of radius 2r can be at most 2 to the n times bigger than a ball of radius 2r, a ball of radius r. So this is sort of the general setting we are considering. And now then there's technical problem, and that is that in this generality, this operator is not guaranteed to be bounded anymore from say L2 to itself, but it's only sort of a conditional result. You have a simpler operator that if that is bounded, then you can prove that this Carlson operator is bounded. So this is to give you sort of an idea of like the way in which we generalize like Carlson's original results. So now in the last time, how much time do I have left? roughly?
Technically 10 minutes, but looking at the
Okay.
number of slides, let's say if we go a few
Yeah,
minutes over,
the
it's
last few slides will be a bit quicker. So, okay, I'll definitely limit myself to 15 minutes, but maybe I'll make 10 because so in the last slides I want to talk about like the formalization and like how that practically happens. So yeah, so this result started when there, so I came to Bonn a year ago and I started discussing with like the harmonic analysis group who were interested in formalization, although they didn't have like experience themselves with it. And I just started discussing like that it would be cool to do a collaboration. And so we decided on this project because yeah, they had just written a preprint about like this generalization of Carleson's theorem. And so they had a paper, and that paper was about 30 pages, and it was like a typical math paper where, like, if you're an expert in the area, like it was a very clear proof. But if you're not an expert in the area, which definitely includes me, then it's very complicated to understand like all the sort of obvious steps that are omitted because like they're standard or they're already yeah, well known, or techniques that you use all the time. And so we sort of had a false start trying to formalize that paper, but it turned out to be like I just had to ask questions all the time, like, oh, what is the step here? What does this mean? And so the group, the harmonic analysis group, decided to write a very detailed blueprint for the formalization, which contains a much more detailed proof and like very precise definitions and many of these techniques written out carefully. And what's really nice is that this allows like people that do not have a harmonic analysis background to start formalizing. Like if you need to know lean, but then actually you can just take a lemma without sort of understanding the global picture of the proof, but you can still formalize it. And it's going really well. So it started, we really started this formalization project process in June, and we're roughly halfway there already. And what's in, yeah, and so it's a non-trivial proof. Like it was originally like 30 pages in the paper, but now in the blueprint that became 120 pages. And then we also added a chapter which is like, or two chapters which is 30 pages to prove like the original, like the classical Carleson's theorem that I from the 60s as a corollary from this general result. And so it's a blueprint that has 11 chapters, which like first the main theorems are stated and carefully defined, and then it's sort of split up into 6 propositions that are like intermediate steps. Chapter 3 proves then Carleson's theorem from these 6 propositions, and then each of the next chapters or sections prove one of these propositions, and those are sort of like parallelized. So the blueprint has also given like a very nice structure to this proof. And I can show you this structure by going to in this website. We're using the blueprint software that was developed by Patrick Passot, and this contains like a LaTeX proof, but also connections with lean proof. So what you see here is a part of all the results. So here at the bottom is classical Carleson's theorem. And then each of these bubbles is like a lemma in the proof. And green means that it's done. And so these parts are all done, but then I scroll out a bit and you see that like there's still like quite a couple of things that are not yet finished. So the white and the blue bubbles means they are not yet done. And so this part is roughly the reduction from the general Carleson's theorem, which is here, to the classical Carleson's theorem. But then there's also here more of the dependency graph with the proof of the general Carleson's theorem, and there you see a lot of things that are not yet done. So one disadvantage of this is we now have like one dependency graph of the whole proof, and so it gets quite big if you want to see the whole thing. But it's kind of nice to see like have a visual indicator of the progress of the proof, and we've now finished like formalized about half of the lemmas, the proofs of them. Just to show a bit of lean code, so this is the statement of this classical Carleson's theorem for the Frea series specifically. So this says, like, let C be a positive real number, let S be a function from R to C. And well, in this case, we're assuming F is continuous and periodic with period C. And then this for all M means like for almost all real numbers X. So for all X up to a set of measure 0, the limit of these partial Fourier sums, so tends to means limit, if like the n of the partial Fourier sum tends to infinity, that is this at top, then this function tends to f of x. So this is maybe a bit hard to read if you haven't seen any lean before, but hopefully it sort of makes sense that all the components are here. Then I also want to quickly flash the general Carleson's theorem, but that is quite a bit more complicated. And yeah, so I mentioned these compatible functions, and then we have this Calderon-Zygmunt kernel K, and then in the end we show that like this Carlson operator like has a norm that is bounded by some things. And then the conditional boundedness is this HT. So we're assuming that there's this other operator that is already bounded, and then the Carlson operator is bounded. Yeah, so let me continue. So one thing that was nice is that I just posted this this project on Lean Sulip chat, and I just said I asked volunteers to help. So what I did was I formalized basically a lot of the statements of the lemmas in Lean, and then I just said, oh, if you want to join and like formalize one of these lemmas, feel free to help. Here's a list of lemmas that don't actually require much analysis. So if you don't know it, you can definitely do those. And so in total, there's now 15 people that have contributed, and the main contributions are from Maria, Inez, Leo, Pietro, Jim, Michael, James, and especially there's a Singaporean guy, Jeremy Tan, who has like done a lot of work on all these formalizations. And yeah, so I'm really grateful to all of them. Yeah, and none of these have a background in Frea analysis, and so this really shows you can really split up like a formalization project like this of like experts that in the mathematical area that write like a blueprint, a detailed blueprint, and then people that know Lean but don't know the mathematics intimately can formalize it. So here is one of the posts that I started with where like I coordinate the tasks. So I have a list of here the first 16 tasks that has now grown to like more than 100. And I describe these tasks, and then people can claim them, and they're either not yet claimed or in progress or already finished. So then, yeah, all of this is coordinated via the Lean Sulip chat. So this also raised some like tricky questions on how to do this. So one question I had at the start was like, oh, will it cause friction that like there's harmonic analysis that don't know Lean and leaners that don't know harmonic analysis? Like, will this go well, or will there just be a communication mismatch? But actually so far it's going great. There is sometimes a bit of tricky things where like lean sort of wants you to formulate mathematics in one particular way if that way fits better like within like mathlib. So sometimes you need to like reformulate some results to make them nicer to formalize in lean. And sometimes that is quite easy, but sometimes that's quite tricky, and then it can also be tricky to know whether that reformulation is actually a good reformulation, or whether you've stated something that is too strong or not strong enough. Another thing that we need to make sure is that like all the formalizations we do here, like all the things that we want to reuse in later formalizations will actually be incorporated into mathlib. And yeah, so mathlib has like high standards for like accepting contributions. And so some parts of the proof I expect will be hard to put into this standard. But for a lot of like the preliminary material that I need and like some earlier results, we intentionally try to formulate them very generally also in lean so that they can be, after we're done or while we're still going, we can port them to mathlib. And one question is to like make sure that everyone like gets credit for their contributions that contributes. So I'm planning to write a paper with at least all the main contributors as authors and acknowledging all the other contributors as well. But it's sort of an open question, like how to like do this well in this project and future projects. Yeah, so some notes on like what this formalization gives you. So one thing, like I don't think anyone doubted that Carleson's theorem was correct. But in mathematical proofs, what you often have is like you have a whole lot of lemmas like in the middle that, and when you read like a mathematical proof very carefully, like quite often, like, oh, some of these intermediate lemmas are wrong or maybe not quite strong enough to prove the next lemma. And so the correctness is here not just of the final result, but it makes sure that like all the lemmas are stated like properly and are strong enough to prove the next thing and are true. Yeah, my view of this formalization and like enabling future formalization is that like I hope on wider adoption and making lean and other proof assistance like easier to formalize your results so that it gets feasible for mathematicians to formalize their own results, and that will like lead to for example, easier peer reviews. Then peer reviewers don't have to check for correctness, just whether it's interesting. I think lean is already showing that it allows for good large-scale collaboration in this Carleson project and also in other projects. And one thing that is nice is lean. It's hard to formalize things in lean. It's still much more work than writing down a LaTeX proof. But actually, lean makes it easier to refactor proofs, because if you change the definition a little bit, lean tells you exactly, oh, these are all the spots where you now have to modify your proofs a bit. Yeah, so let me conclude. So yeah, there's a lot of exciting developments happening in with lean. There's a lot of projects. Of course, my talk is very lean focused. I'm sure there's also a lot of exciting things in other proof assistance. And yeah, large formalization projects can very efficiently be divided into small parts, and then many people can help and join. And yeah, I'm hoping to show once this project is finished that like it's feasible to formalize like hard research problems in harmonic analysis. Thanks for your attention.
Great, thank you so much. Let's thank Floris for this great talk. And we're going to open the floor to questions. We have 25 minutes, so.
I'll ask a question. Thanks, Floris. That was really wonderful. Sounds like a great project. I have a couple of questions about lean. So one is, what happens if there's a lean 5?
Yeah, this question I get quite regularly. Okay, I mean, so you're asking what happens if there's a lean 5, and I mean the answer to that is I don't know. But I can say something about the probability that a lean 5 will happen. I mean, it might happen at some point, but it will not happen in the near future because like lean is written to be very extensible. Like everything in lean is written in lean, so can be like somewhat easily modified and extended. And so there is currently nobody in either like Lean's math community or Lean's core developers that is planning a Lean 5 or realizes that there are like major design limitations that like Lean 4 would not be sufficient.
Okay, that's good to
And-
hear, because I
yeah.
mean, it would be good if there was some kind of commitment to some backward compatibility at some point with lean. Because
Yes,
there have been two big changes, the 2 to 3
yes,
transition.
that is true.
And 3 to 4, yeah.
So yeah, so there's definitely no plans now for Lean 5, and actually like, so neither Lean nor Mavlib are like promising backwards compatibility, but there are steps in the last years to make it more backwards compatible. So like there's both Lean and Mavlib now try to deprecate things before removing or changing them. So if you have like a working formalization in one version, like in the next version, it's like very often you will see like, oh, this function is now deprecated and will be removed a few months later. But it still works for now, and it tells you, oh, this is the new name of the function, things like that. And also Lean like sometimes changes core features, but then has like options to still use the old behavior for a while, and then you have like a longer time spent to modify it. So it's not yet backwards compatible, but yeah, we're moving in that direction.
And then a somewhat related question is, do you see any chance that there'll be some kind of way to use hot in lean directly again, and that the hot community could benefit from all of MathLib or parts of MathLib or something like that?
Yeah, so that is indeed interesting. So I mean, Lean. So one thing that is not implemented in Lean of Lean 4 is the kernel. So the logic that is still implemented in like the original language C++. And I don't think the core development team is really interested in like having a lot of options in the kernel and enabling Lean for that. So in Lean 2, there was this hot mode and standard mode where the kernel was changed, and the main thing was that also sort of all the tactics were compatible with both modes. And that was just a maintenance issue. And I'm also not sure if like now with all the cubicle type theories, like it will take quite a lot of work to use all the like Lean features and use cubicle type. So okay, so this was like sort of the first part. Like if like I don't think the Lean kernel will change, but I think that you can do Homotopy type theory in Lean. In particular, this like groupoid model project I think is very exciting, which tries to formalize like a model of Homotopy type theory or part of Homotopy type theory. You don't get full univariance in the groupoid model, of course. And then you can still write like proofs in this like small proof assistant for Homotopy type theory, and that then will be interpreted as like whatever it means in the internal logic of a category. And then you can still use all of Mavlib and its tools to reason with these like semantic interpretations of the hot objects. So I think that could be a very promising future of like combining Lean and hot.
Okay, great. I see there's several other questions, so I'll let someone else ask one.
So
Yeah, who's
Ali
leading the
is next
question?
on my screen.
Hi, can you hear me?
Yeah.
Thank you very much for the talk. I had a question about the harmonic analysis. When you first started this project, did MATLib have any harmonic analysis, or was this something you had to build up?
Yeah, that's a good question. So there was a little bit of Fourier analysis already. So the definition of Fourier transform and this Fourier inversion theorem in L2 that I mentioned, these kinds of things were already there. But there is also quite a lot of like sort of relatively basic, like sort of master level harmonic analysis that that we still had to prove, well, formalize specifically for this project. So things, so examples of that is if you know harmonic analysis, so there's the Hardy-Littlewood maximal principle we had to formalize. There is real interpolation, or the Markin-Schewitz interpolation theorem that we did for this, and then things like van de Corput lemmas. So there's quite some like quite standard harmonic analysis that we also had to formalize, and we plan to like also port all of these ingredients into MATLib so that they can be reused.
Thank you very much. I mean, this was some of the kind of the difficulty with formalization projects, is that, you know, you have a great idea, you want to formalize it, then you realize all the groundwork is missing. So you have to spend a lot of time doing that, and it takes a lot of time and effort to do that. And by the time you finish, you might not even want to formalize. You want it to do
Yeah, so that I have the same experience, and like so often more than half of the work of a formalization is formalizing all the preliminaries. And that's why in Lean we're building like one library that's sort of one library to rule them all, like one library that can do basically any area of mathematics. And then you hopefully don't run less and less into the problem that, oh, you need this result from this area, this result from this other area, and you can just use them both because they're both in math.
Okay, Emily's next on my screen, so.
Hey, so you mentioned that one of the things you were concerned about is that there would be some sort of tension between the domains experts, the harmonic analysts, and the formalizers who might, want to tweak a statement of a result in the process of formalizing it. And I wonder if you can say anything more about examples where that did happen.
Yes, I mean, so this happened quite a bit. So so for example, the whole chapter on reducing from the general Carlson theorem to the classical Carlson theorem is basically doing a whole lot of analysis on functions with as domain the real numbers. And actually, and so because that is like in the blueprint, it was stated like this. And because that is what we needed. But those kind of things I also want to put into MATLib. And so I want to formulate a lot of these things more generally. So and then the question is, is it true with domain Rn? Is it true with even like a weaker domain, maybe like a Hilbert space or a Banach space? And there's like mathematical questions. Oh, in what of these settings that you can state this in, it's already true. Yeah, and so sometimes I didn't know quite, and then I just stated it for like a generality where I thought, yeah, that is maybe true. Then I wrote a comment like, oh, if you need like a more specific scenario, then you can like weaken the result again because maybe this is false.
So maybe a more specific question. I mean, did you come up with any instances where the tension was caused by the fact that the authors on paper were working in set theory, but Lean is independent type theory?
No, not at all. That is like a complete non-issue because I mean we're so far from like the logical foundations when you're doing analysis. Like it doesn't matter whether you whether like at the basic things are sets or types. It of course matters that you have the axiom of choice. Like if we wouldn't assume the axiom of choice, like we would run into problems.
Well, I mention it just because it seems to be a huge issue for us in category theory because, you know, a category is a dependent type. And so if you ever have to prove equality of something like functors, which sometimes you do when cat is a one category, it's this huge, huge, huge issue.
Yeah, I can. Yes, that is indeed very interesting. That's for
Yeah, so a lot of things
does
are just
matter.
massively more difficult because of, you know, heterogeneous equalities or something like that.
I think a big difference is probably you're using like dependent types a lot, and we are using dependent types very little. So I think that is a big difference between the two projects. That's like basically everything we're doing in this particular project, like we could have done also like in simple type theory, and so therefore we don't run into issues specifically with dependent types. It's it is interesting that you say like in category theory you run into a lot of issues.
I see Carlo next.
Yeah. So I guess I was curious about your thoughts about these blueprints in connection to, you know, like academic credit and things like that. So, I mean, I realize that and these blueprints are kind of common now, right, among like big lean projects. And, you know, there are a lot of practical reasons that you want, you know, to map out what the whole proof looks like sort of before you start, you know, writing tons of code. But at some point, I mean, I'm on this page on your website, and it's like really long and really detailed and just like, you know, basic English, you know, standard mathematical prose, right? And so I guess I wonder, I mean, is there a point at which that itself becomes, you know, a contribution, not just for the end of having a lean proof at you know, at the end, but also just that now there's this new you know, standard proof that maybe fills in gaps, maybe corrects issues, you know, maybe not in this case, but can certainly correct minor issues or you know, fill in minor gaps.
So first a side remark, I didn't mention this, but we definitely filled in like various minor gaps. So we haven't found like any major issue yet. Let's hope that remains the case. But there were definitely like approximations that were different. But so your big question. I mean, I would love if like these blueprints sort of like give you academic credit, but this is like also a question of like people that don't usually. I mean, I'm mostly, of course, in math departments, and like most mathematicians barely know formalization, and they definitely don't really understand like the practical details of formalization. So if you tell them, well, I've written like 20 pages of this like large blueprint, but it's not like published in a mathematical journal, it might get tricky to convince them that this is like valuable. And similarly, it might be tricky to convince journals like, oh, this is a proof that is 5 times as long as maybe you're used to for a proof of this difficulty can be published. That might also it might be tricky to convince journals that that this is publishable material. And I'm also not sure if this is like the right way to consume mathematics for like experts. Like this proof contains way too much details for like an expert to understand, and they are more interested in sort of the big picture idea probably.
Sure. Yeah. But I guess my question is like, do you think that having these kinds of blueprints, or maybe if there's some modified, you know, way that these could be written in a way that would give them, you know, traditional academic value. So like kind of related to how in HOT, as you know, there's, you know, there are various
places where people have unformalized, they write a hot proof and then they
Yes.
write a standard mathematical paper. I mean, not totally standard, but you know what I mean? That's basically saying, well, now that we did that, we learned something. Right. And similarly here, it's like, so, I think the standard, the mathematical standards would be that, if you're just correcting some minor gaps, that wouldn't count as like a normal mathematical publication. But of course, there are situations where clarifying old proofs does rise to the standard of being, publishable. And so I guess, yeah, I just wondered if you had any thoughts about that, or, I certainly take your point that it's too detailed for experts. But, maybe there's a way you can hide some of the, have kind of optional details or,
Yeah, so in this particular case, I think what we're going to do is I mean, probably we're going to publish something close to the original paper. In this case, there was already an original preprint, which was already sort of the length of a normal math paper. And we'll probably publish that with like modifications learned from the blueprint, likely. So, but you can imagine if you just have a blueprint that you sort of like unformalize the blueprint in the sense of like just reducing the length by cutting like eagerly a lot of things. So, and then try to publish that. So yeah, I think that might become a practice with these kinds of formalization projects.
Sure, yeah.
I see that there's a lot of messages in chat. I haven't read any of them. So I don't know if there's questions in there.
I think there were questions, but they were answered in a way.
Yeah.
There were also answers in the chat.
Okay.
Unless I missed something that, I maybe add one more comment, like going to different math departments in North America. I noticed that for a lot of mathematicians, formalization equals lean. These days, when I try to tell them I do homotopy type theory, they ask, okay, what's that? I mentioned something about formalization, and they say, oh, the lean thing.
I have also noticed that. I wasn't sure if that was also due to like how do you call it, sampling bias? Like I am there talking about lean, but I think one reason for that is that like there's just a lot of exciting things happening in lean, and lean is growing so quickly that like mathematicians are getting more excited about lean.
I blame Terry Tao.
Yes, the fact that Terry Tao has gotten somewhat addicted to lean definitely helps.
Yeah. Okay.
Can I ask another question? So you mentioned about 50% of the blueprint is formalized now. I'm wondering, of that 50%, what percent has been ported into MATLAB or is on its way into MATLAB? Or are you waiting until the end, or how is?
Yeah, that is practically nothing. I don't necessarily want to wait until the end, but I have not like focused on porting to MATLAB yet. So that is definitely something I want to do before like the project ends as well, but I haven't done that, like focused on that yet.
Mm-hmm.
Okay, fantastic. So if we have no further questions, then we can finish 5 minutes ahead of time. So let's thank Floris again.